Welcome friends. The topic for today's discussion is expectation value and operators. Before we try to understand the expectation value, we would like to first of all understand the meaning of weighted average. So say for example you have a class of a few students and the distribution of marks among the students is something like this. 10 students have obtained 70 marks, 25 students have obtained 65 marks, 30 students have obtained 60 marks, and so on. So if this is the marks distribution, then the average marks obtained by the student can be calculated by this formula, where we multiply the number of students with the marks obtained, take the summation, and then divide it by the total number of students. So by doing this, we end up with this formula where marks average is equal to the summation of ni into xi divided by the summation of ni, where n is the number of students and x is the marks obtained. Now we just want to rearrange this particular formula and try to see that how we can represent it in a different form. So let us ask a question that what is the probability that a student gets 55 marks. So here we can see that 27 students have obtained 55 marks out of 133 students. So the probability of getting 55 marks is 27 by 133. Similarly, for every term in this expression, we can calculate this probability. So 70 marks into the probability of getting 70 marks plus 65 into probability of getting 65 and so on. That becomes the average marks. So the marks average will be equal to the summation of the marks obtained into the probability of student getting that particular value. Now this particular equation is true when the value of n is an integer or the value of n is discrete. But if the value of n is continuous, then the summation would change into the integration, and the weighted average in the integral form is nothing but the expectation value. So we wanted to understand what is expectation value. The expectation value of x is nothing but the integration of x into probability of occurrence of x into dx. Now let us apply this to the quantum mechanical system, and here we find that the probability is replaced by psi square, because psi square gives the probability of occurrence of the particle in a particular place. So we have expectation value of x is equal to psi star x psi dx. So this is how we compute the expectation value. The same procedure can be used for other functions of x like gx. Then the probability of gx is equal to gx into psi square dx. So for instance, if you want to find out the expectation value of potential energy, then you just replace the x with ux and you will get the expectation value. Now the expectation value of momentum of a particle cannot be calculated in the same way as we have done in case of potential energy, because according to the uncertainty principle, you cannot find a function px, since x and p, they both cannot be predicted with 100% accuracy. There is an uncertainty in position, there is an uncertainty in momentum, and therefore to compute the expectation value of momentum, we have to employ a different method. Similar is the case with the energy and time. So we will see how we can find out the expectation values of energy and momentum. So let us start with the wave function. Psi xt is equal to a into e raised to I upon h cut e t minus px. This is the wave function which we have assumed, and on the basis of this, if we take the first differentiation, we will get d psi by dt is equal to the wave function itself multiplied by the differentiation of the exponent. So when you differentiate the exponent with respect to t, then the x term will become 0 and only e will survive. So it is minus I h cut by e. So d psi by dt is equal to minus I upon h cut e psi. Or we can write e psi is equal to minus h cut upon I d psi by dt. Just bringing the iota in the numerator, we will get the expression as e psi is equal to I h cut d psi by dt. So let us mark this as first equation. We will now go to the wave function once again and differentiate with respect to x, and we will get the momentum over here, and you find that d psi by dx is equal to I upon h cut p psi. And this brings us to the expression where we write down p psi is equal to h cut by I d psi by dx. So we have got two expressions. One is e psi and the other is for p psi. Now both the expressions we will write down, and from these expressions we will try to find out how we can evaluate the value of energy and momentum. So we have the equations for E psi and P psi. We'll just put the psi outside the differentiation. So E psi is equal to I h cut d by dt of psi, and P psi is equal to h cut by I d by dx of psi. As a result, we find that E is equal to I h cut d by dt and P is equal to minus I h cut d by dx. This minus sign has appeared just because we are taking the iota in the numerator. So we can represent those two equations in simple form of energy operator and momentum operator. So when we will operate this function over the psi, we will get the energy of the system. When we operate this function over psi, we will get the momentum of the system, and therefore this is called the energy operator of the system, and this is called the momentum operator of the system. So now we have got the operator for momentum. We will try to find out what is the expectation value, because finally we are interested in that. We have the operator on momentum and we operate it on psi. So the expectation value of P, the momentum, is given by psi star P caret, that is the momentum operator, and psi, and this is the expression over here. So this is how you find out the momentum of the system or the energy of the system. Similarly, we can derive the other operators also. Say for example, the kinetic energy operator can be easily derived. We have got kinetic energy is equal to half mv square. Half mv square and multiply and divide by m, we get p square by 2m, and p we know, the momentum operator we know, so just square it and we get the p square by 2m. This is equal to minus h cut square by 2m d square psi by dx square. Here in kinetic energy operator you find that the complex value is gone because you square the momentum, and therefore we have the real value of kinetic energy. So we have found out the energy operator, the momentum operator, and the kinetic energy operator. Let us go ahead with the Schrodinger's equation. Then we have the equation represented, the Schrodinger's time dependent equation represented like this, where psi is the function of position and the time. Then this can be rewritten as the energy operator, I h cut d by dt of psi, where this is your energy operator, and this is your kinetic energy operator, and this is your potential energy operator. So the total energy is kinetic energy plus the potential energy, and this becomes, this whole thing, kinetic energy operator plus the potential energy operator, that becomes the Hamiltonian of the system. This is called the Hamiltonian of the system. So we have got energy E psi is equal to H psi. So this is one of the representations of the Schrodinger's equation. Thank you very much.